this lab, we looked again at charged tapes, but we used a different computational model to glean more accurate results. The purpose of this lab is to revisit the experiment we did for Lab 1 and improve the accuracy of the computational model we used to find the electric force of the bottom tape on the top tape. This was done by instead modeling the tape as a distributed charge, not as a point charge, as done in Lab 1. The program found the magnitude of the electric force and the magnitude of the gravitational force to be 1.962 e to the negative 3 newtons. The charge of the tape was found to be 1.88 e to the negative 8 coulombs. Here are the physical principles we used. We used that in static equilibrium, F net equals 0, and in our case, there were two forces that canceled each other out, gravitational and electric. So we knew that the electric force would be equal and opposite to the gravitational force. The electric field equation is kq over r squared, and the electric force equation is E times q. In addition to these principles, which were also used in Lab 1, we used integration to calculate the total electric field of the tape modeled as a distributed charge. Below is the E-rod equation set to equal to the force of gravity. This is mg equals kq squared over r times the square root of L squared over 4 plus r squared. We use this equation to find q. Instead of modeling the tape as a point charge, with charge concentrated at its center, in this lab we will model the tape with its charge evenly distributed across its surface. This will give us a more accurate approximation of the electric field of the tape and also the overall charge of the tape. For our physical principles, Newton's second law and the electric and gravitational force equations were used as they were in the last lab to approximate the electric force. In contrast from the last lab, we used the distributed charge formula to find the electric field of a modeled rod, which better approximates the shape of the tape, to find the charge of the tape, Q. Here's our experimental overview, shown on the right. The system was the tape on the top, and the surroundings was the tape on the bottom and the earth. We used the same procedure as Lab 1. We charged a tape of known length and measured the distance at which the charge from the bottom tape caused the top tape to become suspended. Here are our initial conditions and assumptions. The separation distance was 0.016 meters, the mass of the tape was 0.0002 kilograms, the length of the tape was 0.2 meters, K is 9 e to the 9, and G is 9.81. The assumptions we had were to ignore air resistance on the moving tape. We also assumed that both tapes have about the same amount of charge and that charge is evenly distributed along the length of the tape. The code worked by first finding the electric field produced by the tape using the same methodology from Lab 1. A for loop was then used to iterate through each piece of charge in the bottom tape, calculating the electric field and then the electric force at the location of the top tape due to the bottom tape. Arrows were created for each of the iterations. Arrows were also created to depict the overall force of gravity and the overall electric force. Here are our results. The red circles model the top tape, while the blue model the bottom tape. The white arrow shows the overall electric force, while the yellow shows the force of gravity. The green arrows are the individual electric forces of each iteration of the bottom tape on the top tape. We found that the magnitude of the electric force was equal to the magnitude of the gravitational force, and this was 1.962 e to the negative 3 newtons. We found the charge of the tape to be 1.88 e to the negative 8 coulombs. Some possible errors were the handling of the tape could have affected the charge due to electron transfer. There were also simplifications of the model. We treated the tape as a one-dimensional rod, and it's actually two-dimensional in real life. These differences between the model and the reality could have caused, or the assumptions we made could have caused differences between the model and the reality. This model output will not be exactly the same as observational data. Along with modeling the tape as a one-dimensional rod, the charge we gleaned from our code is probably not 100% accurate. What if the tapes were modeled as point charges? In Lab 1, when we modeled the tapes as point charges, we found the charge of the tape to be 7.47 e to the negative 9 coulombs. In this lab, we found the charge to be 1.88 e to the negative 8 coulombs. Modeling the tape as a point charge in Lab 1 decreased the predicted charge of the tape by almost 40%, meaning it was an underestimate. Why do these estimates differ, and which is more accurate? The distributed charge model is more accurate in that it doesn't treat the tape as a point charge. Because we made the model more advanced and closer to the charge of the tape in reality by iterating across the length of the tape, it gives an answer that is more likely to be correct.